So then our next speaker is Ignacio Ruiz from IFT in Madrid, and he's talking about a taxonomy of infinite distance limits. So please go ahead. You're muted, Nacho.
Okay, thanks. I would like to start by thanking the organizers for letting me know that I was muted, and also for allowing me to speak in this session of the String Fino seminars, in which I would like to present some paper that hopefully it will be out soon, written in collaboration with Mulder Wethridge, Beit Heinrich, Tom Rudelius, and my supervisor, Irene Valenzuela. As you can see from the title, infinite distance limits are going to be of importance to us, so let's first introduce them. So as you may know, in string theory and any other like lower energy effective field theory that we might derive from it, we don't have like continuous parameters, but rather they are the back-in expectation values of some scalar fields that we call moduli in the case that they are massless. And we can read from their kinetic term a metric that is a metric of the moduli space of the values that these parameters can take. We can also consider like some small potential that might give these scalars some mass. In principle, there's nothing wrong with that. And what will be interesting for us is the perturbative regimes in which some of these parameters are small, and they are usually related to infinite distance limits with respect to the distance that we might take along some trajectory in moduli space. These different limits might have some microscopic nature that we might know, and as we will see in this presentation, by knowing what is the nature of these different limits, we will be able to constrain how they all fit together in a global form around the asymptotic regions of the moduli space. Will be able to give us information about like the different prescriptions or duality frames and how do they fit together. So let's get to it. So as we are dealing with infinite distance, what comes to our mind is the distance conjecture by Oguri and Baffa that states that every time we are traveling such a long distance in moduli space, we will encounter a tower of an infinite number of states that are becoming light exponentially with this distance that we're traveling. This has been tested in many papers, in many scenarios by many people. I try to put all of them here, but I'm sure that I missed somebody. But on principle, this value of the order one parameter is not set, but that's what the sharpened distance conjecture suggested, that it has to be always larger than 1 over square root of d minus 2, which is the value that usually corresponds with emergent string limit, while larger values could correspond to KK the compactifications, as it is expected from the emergent string conjecture that we will use later. On the other hand, from the weak gravity conjecture by Palti, if we have the mass term in the Lagrangian of these light towers, one could expand in a derivative expansion this mass, and one can interpret this derivative of the mass with respect to the moduli as some Yukawa scalar charge between the scalar and the fields, which allows us to define the scalar charge to mass ratio vectors by just the derivative of the logarithm of the mass with respect to the different moduli that we have in our moduli space. From it, we can obtain the exponential rate just by multiplying the tangent vector in the direction that we're going, normalized tangent vector, with respect to this scalar charge to mass ratio vector. And from the sharpened distance conjecture, would expect that if in any direction the exponential rate of the lightest tower is given by the tower that is projecting that has a larger projection along this direction, then we would expect that in order for this to be always larger than 1 over square root of d minus 2, we'd expect the value that is centered at origin that has this radius to be inside of this whole span by the different vectors of the different towers. So on principle, one could think that this is the only restriction that the shape of the different vectors might have, but as we will see, this is not the case. We will show that under some assumptions that we will argue for, there are some taxonomy rules that tell us how the different limits, the different towers fit among each other in such a way that we can put them together in a finite way that we can do in a systematic way, this classification. So far, I've been only talking about the lightest tower, but one, as David said, one also has another scale, which is the species scale, and the scale at which gravity becomes strongly coupled. That also depends on the moduli of our moduli space. So one could also define these scalar Taxonomy ratio vectors for this species scale, as they are telling us which is like the effects that are becoming are making gravity strongly coupled. They will give us information about the duality frames of the theory that we are moving towards as we are going to infinity. So let's get with taxonomy rules. Our starting point is the emergent string conjecture, which also David stated that in any limit, what we will get is either a tower of weakly coupled string oscillator Morse or a KK tower. Once we interpret this from the species scale point of view, this will be given asymptotically either by a higher dimensional Planck mass or the string mass. We will impose some restrictions in this decompactification limit that we are decompactifying to a warp limit. This is that the volume of that we are decompactifying is homogeneous, so it doesn't depend on several terms that might compete among themselves. Or, for example, we are not decompactifying to a running solution, but rather to a vacuum. And when we have several towers that are becoming light at the same rate, they can form bound states. Let's get a little bit more into this. So, for example, imagine that you have two cycles that you can decompactify, one of n dimensions, another of m dimensions, and in some direction, they are becoming light at the same rate. What we're saying is that we are expecting that we are actually decompactifying m plus n dimensions. So our KK states can be charted not only under n or m, but rather under any of these these dimensions that we are decompactifying, such that at the end we are having a much larger number of values of states becoming light, such that the species scale is given by the Planck mass of the total dimension that we are decompactifying towards. Another possibility is that, for example, if we have some theory on a circle, some theory on a circle, and we have KK and winding modes along some direction, they will become light at the same rate. But rather than having like true compactification or the compactification of two dimensions, what we are having is that we are actually moving towards an emergent string limit, which this gives us both the lightest tower and also the species scale. If this was not to happen, as we'll see, then the angles, the possible arrangement of these different vectors could be on principle arbitrary, and we would not be able to follow our program. So just by a simple compactification exercise, one finds that the KK tower that appears after compactifying in some d plus n dimensional theory and volume, and in compact volume, the exponential rate or the length of the scalar Taxonomy ratio vector of this KK tower is given by this expression, while by the universal relation between the string tension and the dilaton, we expect that the scalar Taxonomy ratio vector for the string tower to have this expression. On the other hand, if we further compactify with another volume, that we will obtain that the new tower with respect to this one, and if we multiply them, we will always get 1 over t minus 2. So by having the lengths and the product, we can restrict the possibilities for the angles between these two towers, both between two KKs and a KK and a string tower. It's also worth mentioning that in both expressions, when we go to in the KKs, we send one of the n to infinity, what we recover is the expressions for the emergent string limits. So at least for these taxonomy purposes, we could understand the emergent string tower vertices as just the compactification of an infinite number of internal dimensions, although this is not what is happening actually. Furthermore, if we do not have that, if we have that this doesn't only apply in a given direction, but actually we have some asymptotic flat slice of our moduli space, such that these vectors are tangent to it and are also constant, they are not moving, then these different angles and limits, they can be glued to each other. And as we have a finite set of possible angles and length, we will also get a finite number of ways of gluing all these things together. This will be our classification. This so far has been only been about the lightest tower, but in principle, one could obtain these taxonomy rules also for the species scale scalar mass ratio vectors. And one could, on principle, do the same. But as we showed in a paper with Alberto Castellano and Irene Valenzuela last fall, there seems to be some pattern between the lightest tower and the species scale that not only includes states from this lighter tower, but also from possibly subleading towers. We obtain that the product of the two vectors seems to be always 1 over d minus 2. This holds always under the assumptions that we have considered for this taxonomy, although in principle they are more general. And the result is that the convex hull, the polytopes that we build from the species scale vectors and the light tower vectors, they are actually dual with respect to the sphere of this radius. So on principle, if we had one, for example, this is one of the examples that we get in, actually the only example in 9D with two scalars, this triangle for the light towers, by obtaining the dual polytope with respect with the sphere of radius 1 over square root of 7, which is the same circle here and here, what we get is the polytope for the species, where we can identify the string mass and the different Planck masses. So in principle, once we classify our tower polytopes, we will have by free the different species polytopes. So let's get to show some examples and some applications. So the first thing that comes into mind when one tries to apply these taxonomy rules is to apply this just when you have two moduli. So we will be working in two-dimensional flat slices of moduli space, where these polytopes are just polygons, so they can be identified by the number of the compactifications that we are doing in each vertex. Furthermore, we will ask that we are decompactifying to at most 11 dimensions, so at most M theory, and that in these 11 dimensions, we don't have any string living. Then what we can do is all these possible angles, we add them together, and they should add up to 2 pi. So this is the results that we get. For example, we get a single example. That's the one I showed you before. In 9D, we get 2 examples in 8 or 7D, but actually in 6D, and if we went down further to 5 and 4, we would get like many examples of these. Most of them can be actually obtained in different string or in theory compactifications, but some of them that we will come back to later, no. For example, this one or this one from this row. The difference in 6D between this row and this one is that every time we have like an edge of this polygon in which there's an emergent string limit, the KKs at each side are of the same type. But this is not the case in these for this row, in which we on principle allowed for different decompactifications at each side of the emergent string limit. We will come back to this later. Other thing that one can think is that by starting in 11D supergravity, we compactify in an torus, so we have n radians that will be our scalars, and see what are the possibilities. In 10D, we have 3, as we have just two possible vertices, the emergent string limit and the compactification to 11D, and they don't need to fit together because they are in opposite directions. We have these 3 possibilities. One is the one that we obtain in type 2A, in which we have a weak coupling string limit and also the compactification to M theory. The other one in type 2B, type 1 orthotic, in which we have 2 emergent string limit that are, in a sense, dual to each other. And finally, the taxonomy rules will allow for 2 opposite decompactification limits to M theory, or to an 11D theory, but we do not know of any actual 10D theory that features this. If we go to 19, that's again the figure that I showed you before. One obtains the same triangle. There's a unique one, so we wouldn't expect anything else. But it is interesting that, for example, once we, in this case, it's more interesting the string, the species scale polytope, and depending on which is the species scale that dominates in each of the asymptotic limits, we get either a string theory in 10 dimensions or a supergravity in 11D. The range of validity, so the range of directions in which this duality frame will be the appropriate description, is also set by these taxonomy rules, as they will tell us which is the different angles in which the the different vertices of the species scale polytope will dominate. So this is also interesting that these angles are somehow also quantized. If we go to a D, then we again get a single polytope, but it was also observed in past papers, featuring both emergent string limit and the compactifications to 1, 2, or 3 more dimensions. One could go down to 7, 6, 5. The more we go down, the more complicated they are to picture in a flat screen. But the taxonomy rules allow us to get the specific vectors, coordinates, and relations between the different towers. And actually, this is what we would get from compactifying M theory on different tora. We can do something that instead of compactifying down, we could go up. So if we have some compactification that allows for an intermediate decompactification, first one cycle, then another one, etc., we will be able to iteratively recover the different polytopes of the higher dimensions. And what is also interesting is that they are going to lay at the height of the species scale of the theory that we are moving towards. In 9D, we have the two of the KK limits are inequivalent, this one and this two. And depending on where we're moving, we will recover the polytope associated to type 2b, for example, or to type 2a. One can do the same in 8D, where we have that all the KK limits of the compactifying just one dimension are equivalent. And if we move to one of them, we will recover this unique vector polytope of vectors in 9D that again lay at the height of the 9-dimensional Planck mass, which is where we're moving towards. If we decompactify not one by 2 dimensions in 8D, we have that there are two inequivalent limits. One would be this, and the other one's this. And depending on where we're moving towards, we will recover again the type 2b polytope in 10D or the type 2a. It's interesting that if we try to go directly to 11D, so moving in this KK3 direction, at the height of the 11-dimensional Planck mass, there are no towers, which is indeed what one expects. So one doesn't have a non-compact moduli space in 11D that would feature asymptotically light towers. So we don't get them. And okay, so far all the examples that I've been showing you are without warping. This is that the vectors remain fixed, but on principle, we do not expect this to be the case. We will expect that in some limits, we might be decompactifying to some prime solution, or the volume that it's getting large is not homogeneous. We have several terms competing. But in any case, we expect these special directions to be of measure zero in the set of like possible infinite distance limits. And along these directions, the vectors, I will show you now an example, are going to slide perpendicularly to the direction that we're moving, which will result in the exponential rate of these towers being preserved. Once we move far or slightly off in the direction from this locus in which we are getting the sliding, we will recover some of the polytopes that are classified by a taxonomy rule. So one could interpret this sliding as a perpendicular interpolation between different polytopes from the taxonomy. One example of this was described in this paper from last year by the authors of the paper plus Jake McNamara, in which we compactified a heterotic theory, the heterotic on a circle. And when one goes to the duality frame that is better described by type 1 prime theory, we get that there's a self-dual line, and when we are not moving parallel to it, we get our normal 9D triangle that we are most familiar with. But once we start moving parallel to this self-dual line, depending on the distance to it, we will see that this KK tower will slide until it crosses the self-dual line, as we also cross it, and we move into the dual type 1 prime frame. Once we are far enough from it, we will recover again our triangle that is just turned around. That's the same shape and vectors. As you see, this sliding is perpendicular, so we have just like going from one description to each other by moving the tower in a perpendicular. So let's go back to...
Nacho, sorry.
Yeah.
5 minutes until question time.
Yeah, no problem. So if there are no questions with the examples I showed so far, I will get into the examples that we do not know whether they exist or we just haven't been able to find them. So one of them was the 60 polytope, D equals 6 polytope, in which we had on principle symmetry between the AKs at both sides of the emergent string limits, but that we said that we weren't able to find any string or in theory compactification. And if one tried to compactify it to 5 dimensions, it could be, one could see that this is actually not possible. There are no taxonomy good enough polytopes in 5 dimensions such that this can be recovered by the compactifying it, but one obtains it from a polytope in 4 dimensions that, as you see here, well, green is the compactifying 2, orange is the compactifying 4, maroon is the compactifying 6, and the red are the emergent string limits. We just go up as we decompactify in pairs, not to any odd dimensional theory. And as for the other ones that we didn't see, that are the ones that we have, that they are not symmetric with respect to emergent string limit in these edges. On principle, on the top of our heads, there's nothing wrong with them, but the fact that none of them are observed in different constructions suggests us that there might be something iffy with them. Maybe a worldsheet approach to see if there's if they are consistent or they are in the swampland could be appropriate. And before finishing, I would like to stop a little bit with this one here that actually is related to, if you recall, to the 10-dimensional polytope featuring to the compactification limits, because if we start with this and we decompactify to 10 dimensions, what we get is this polytope. So maybe whether there's something fundamentally wrong with both of them or if they are just some unknown corner or the string landscape is related in this case, in these two cases, okay? So, to conclude, we have shown that the emergent string limit not only tells us about the different possibilities for the light towers that one might get on the species scale, but rather how they fit under some mild assumptions among each other. So it can tell us a lot about like the global asymptotic picture of our moduli space. As for where to take this farther, as we have seen, one possibility would be like to fully understand how sliding works and the different possibilities of it and the interpolations, and also going to non-flat moduli space, maybe by the inclusion of actions or other compact scalars, where we no longer have a global flat manifold or a scalar manifold, or maybe it is not complete. So one might be able to have to work with different local frames. As for the non-observed examples, I urge the audience to maybe look into, tell me if they have any ideas about where they could come from, or maybe just the assumptions that we took need to be tightened so that we do not get these strange figures. So if you had to learn something from this talk, it's like how strong the emergent string conjecture is for the different asymptotic limits of our theories, and also that some program by using swampland dualities can be carried out to get like the different possibilities of the in the set of possible asymptotic duality frames that one gets. This is also in line, although we do not do the same with what Alec Droya and Yuta Hamada did on a paper from last year. So it seems like a promising avenue. Thanks a lot.
Okay, so thank you very much for the very nice talk. Are there any questions from the people online? Well, maybe while we wait, I can already ask a question. So did I get correctly that what you said, that lowering supersymmetry and therefore effectively including the sliding and so on, always what it does is effectively interpolate between the maximal supergravity, sorry, the polytopes that are allowed in the maximal supergravity case? Is this was the statement, right?
Yes, I mean they appear without sliding in supergravity, but we are not assuming supergravity, at least when applying the taxonomy rules. So yes, I would say that with enough supergravity you don't get sliding, and that when you do have this sliding, it always occurs between already classified things. Another possibility, I haven't gotten into that, is that maybe when you have this sliding, one of the towers, one of the directions ceases to exist. Maybe this tower just doesn't exist in some limit that you're taking, and maybe you are interpolating between polytopes of different dimensionality, but they are in any case described by the taxonomy rules.
Okay, but it's clear that somehow it is always interpolating between the
polytopes and in a perpendicular way, so you don't get anything weird happening with the exponential rate.
Okay. Thank you. So we have another question from Harvard.
Yeah, question from Naomi.
Hi, thanks for the talk. I had a question. Do you have any idea of the scaling of the number of possibilities for this taxonomy as you go down in dimensions?
So I guess you're thinking about, this, the table, right?
Yeah, exactly.
Okay, so I'm cheating a little bit here in the sense that we are putting here just the ones that we obtained. For 5D, we got some possibilities. But actually the computer was taking too long, and at some point we stopped because they were already like too much. So we guess it maybe grows exponentially, but that's just guessing. As for once you have larger number of polytopes, it seems that if you're in d dimensions plus n possible radians adding to 11, apart from these three, you always get one. So this is the unique one, this is the unique one, these two are the unique ones. You can then get slices of these large polytopes and get smaller dimensional polytopes, and then you can get fewer of them, but they are not unique either.
I'm just wondering how it compares, for example, to the number of Calabi-Yaos in different dimensions.
Okay, yeah, so we also have some work on Calabi-Yaos. It's a little bit tricky because if you're just working in a specific Keller cone or some chamber, you can also apply taxonomy rules to the towers that you're getting there, but you are not going to complete the whole Rn if you are with n moduli. And what you will get is somehow the different angles that you can get once you go to the properly normalized moduli in this chamber are always going to be constrained by the taxonomy. So yeah, there's for sure some taxonomy work that it could be done on these Calabi-Yau compactifications and how they fit together once you do some flop or something.
Okay, so I think we had another question from Harvard first, and then Eran.
Yes. Thanks for the talk. I was wondering about this possibility that you mentioned of having two limits to higher dimensional theories in 10 dimensions, and that we don't have an example of that. But how would you imagine this even being possible? Because that would be something like having T-duality in M theory. And if you assume that this cannot happen, does this affect your subsequent analysis?
Yeah, so for sure, this is just an example of maybe taxonomy is too lenient. So maybe if we just throw a computer the taxonomy rules, it's gonna return to us some things that don't make sense. Yeah, regarding to what we commented here at the end. Yeah, for sure these two are related. So if this one was to actually appear on some compactification, we would be able to recover that thing. So maybe that this is pretty strange it means that we cannot have this one not either. But for the other 5, apart from like, yeah, there's something strange about this not symmetry thing. We don't have any concrete argument on why this could be wrong.
I see, thank you.
Okay, so then one last question from Eran.
Hi, thanks for the talk. It's very nice. I have a question. So scalar fields, they don't have a canonical dimension object that they couple to, unlike, let's say, a gauge field canonically coupled to a particle and so on. So when you ask about what states become light, they needn't necessarily be particle states. For example, even emergent string limits, you can ask the question, when you calculate this psi, you are calculating the coupling to the oscillator modes, presumably. But you could also ask the question, what about it coupling to the string itself? And this coupling differs a little bit. And I was wondering if you studied these kind of vectors, which are defined by the coupling of the extended objects rather than the particles to the scalar fields.
Yeah, so in this, okay, thanks for the question. In this work, we only consider particles and like as some degenerate limit, also like the strings, because they are important per se. But I do know that there's some work, ongoing work, on trying to generalize these couplings and these scalar mass ratio vectors to higher dimensional extended objects. I do think that Ben and Muldrow and Tom are working on this, but we do not include results from that in this work.
Because I think that if you do, then I think there's probably some bound, like something like the gravity is the weakest force on some object, which seems to be violated. For example, like if you take like the F theory limits, like in a kind of compactification that like sort of Timo and Wolfgang and Sungju studied, they found some small factor violations of kind of gravity being the weakest force. But they're looking at the coupling of the oscillator modes of the string. But if you compactify them to 4 dimensions, those oscillator modes are non-BPS, but the string would give you BPS particles. And then you can prove in 4 dimensions that BPS particles do satisfy such a gravity weakest force bound. So I would expect that high dimension objects do satisfy it. So I think if you look at the high dimensional ones, you would expect to see some bound on the side.
I guess on the other hand, we are only studying like towers that at some point are becoming like the leading ones. So I don't know if like these extended objects at some point will be like the leading towers. Maybe they could be included, but
not necessarily the leading one.
Yeah, you would have maybe to put some extra assumptions on the taxonomy.
All right. I just wanted to ask about this extended one. Okay, thank you.
Thanks.
Okay, so then maybe we can close the session here. And first, let's thank again Ignacio and David for the very nice talks. And well, as usual, now we will stop the recording and we will leave the Zoom open if anyone wants to